Line up today for the afternoon session. We will begin with Fateh and Mekdour talking about polymultiplicatives and polymorphisms. So, Fateh, are you ready to present?
Yeah, I'm ready. Hello,
okay,
everybody.
Fantastic.
Are you here all? Do you hear me?
I can hear you.
Can you hear me?
Can anyone else hear?
Yes, we hear you very well.
Okay, good.
But he needs to share his screen.
Yeah, okay. It's okay. So, is my screen appears clearly?
Yes, this is good.
Okay.
All right.
So, firstly, thank you, Mr. Jonathan. Are you ready to start or no?
So, yes, should be fine to go now.
Okay.
Is everybody ready? We are a minute earlier. I suppose we can wait half a minute. We can go. Is everybody ready?
Wait, just to show my camera.
Okay, let's go.
Okay, so in the first, I want to thank all the attendees in this conference, especially all the organizers of this conference, to give me this opportunity for my first participation. So I'm very honored to be with you. Let me present myself firstly. I'm Fateh Mekdour, PhD student at the Faculty of Science, University of Tunis al-Manar, Tunisia. My talk today is about the polymultiplicatives and polymorphisms. Of course, this joint work with my professor, Milou Chil. So let me explain the title of this talk, where we take that the algebra homomorphism to a new version, or let me say a new class, which of homogeneous polynomials P, which called polymultiplicative. We provide some characteristics to describe that relation between these classes and the class of polymorphisms. So firstly, let me give some necessary notations that related in this work. So the real space A is said to be a real algebra or lattice ordered algebra if there exists an associated multiplication in A with the usual algebra properties such that the product of positive elements belongs to the positive cone or still in the positive cone of A. Such a real algebra A is called F algebra whenever that disjoint element F and G implies that F and H, FH, the product FH and G are disjoint, and also that the product HF and G are also disjoint for all H in the positive cone of A. No zero linear functionality on an arbitrary real algebra A is called an algebra homomorphism on A if T is multiplicative. That is to say that T preserves the multiplicativity for all element F and G in A. An operator T between real spaces E and F is said to be a lattice homomorphism whenever that T preserves the lattice operation, or we say that T preserve the modulus for every F in A. So that equivalent to T preserves the lattice operation as we know, the suprema and infinima. Our main interests in this work as the following ideas. So the main purpose of this work is originally motivated by the study of homomorphism on functional algebra spaces in order to give a new class called polymultiplicative for homogeneous polynomials P. Secondly, it presents some analogous and generalized result of Garrido, Gomez, and Yaramilou about their study about the evaluating properties of a linear homomorphism on functional algebra spaces to extend that for both multilinear and polynomial cases under some principal conditions. We are interested with polymorphisms which are under certain conditions polymultiplicative or polymultiplicatives. Let's firstly, we define that. What does it mean by cohomogeneous polynomial P between real spaces A and F is a polymorphism if and only if P preserves the modulus for every F in A. Now, in the following context, let me present that most previous works that related to this topic. As we know, or in our knowledge, the F algebra is reaching its structure, which has both algebraic structure and lattice structure. Hence, it is a natural impetus to study the link between the mapping that preserves the algebraic structure, which called algebra homomorphism or multiplicative mapping, and the one that preserves the lattice structure, which called lattice homomorphism. This topic has gained wide attention by several researchers in the last few decades, such that in 1977, the first result in this direction appears to be due to Hager and Robertson, who have demonstrated that if A and B are two Archimedean united algebras, then any reads homomorphism T between A and B that preserves identity is automatically a multiplicative homomorphism. One of the other important results in this aspect is given by Van Boten, who presents specifically a reads homomorphism that preserves identity on F algebra are precisely the extremal point of the convex set of all Markov operators. Here, the Markov operators, which we know that the set denotes by the set of all positive linear operators that preserve the identity. Next, Boulabier and Toomey generalized the theory of both Hager, Robertson, and Van Boten in the bilinear case. Other authors on this topic have provided some necessary and sufficient condition of or for the equivalence between the reads homomorphism and multiplicative homomorphisms on F algebras, which have been also provided by Hodgman and de Bachter. Moreover, the last analogous result was generalized to the multilinear case by Karim Boulabier. Now to dive in our matter, let first we introduce the following definition. If we take A, let's take A is the subalgebra of Rx. Here Rx is denoted by the set of all real valued functions on an empty set X, which we know that the Rx is commutative and associative algebra under the usual pointwise operation. And P is a cohomogeneous polynomial defined on A. We say that P is a polymultiplicative. If for all F and G in A, we have that P preserves the multiplicativity. In the remark below, it's obviously that if we take that phi, it's the associated symmetrical linear mapping of P of B, and phi is a multiplicative, then P is a polymultiplicative. Let we keep the notation that throughout of this work, F power n, that means F times F for n times. As a simple example for this classes of polymultiplicatives polynomials, We take that A be a subalgebra of Rx and be defined on A with the real value by defined by that the nth power of F. Then it's clear B is a polymultiplicative. Now let we insert respectively that the definition of M evaluating and M bar evaluating of the symmetrical linear functional on arbitrarily a subalgebra of Rx. So let me take AB subalgebra of Rx and phi be a symmetrical linear functional defined on A. Defined with A, let M be a natural number and K is also greater than or equals to. Phi is said to be M evaluating if for every subset B of A, with that M refers the cardinal number of the k-fold Cartesian product B, then there exists X in X such that the following identity holds. That means the value of phi of F1 Fk, it can be represented by that the product F1 Fk in X for all the k-tuples of elements F1 Fk in the k-fold Cartesian product B. By similar way, we define that phi is said to be M bar evaluating by the same assumption. And for every strictly positive element, then there exists X in X such that we can approach the value of phi by the product F1 Fk in X. Likewise, we denote that the definition of M evaluating and respectively M bar evaluating of k-homogeneous polynomials P by similar way and the same assumption, we get the following identities. Let we return to the previous definition. Just we give a remark. We look for the previous definition. So here that it's easy to see that every M evaluating is M bar evaluating. Not difficult to see that. Now we show one of the properties in the following proposition. We show one of the properties of that the symmetrical linear functional phi, that phi defined on the subalgebra A of Rx, which is a no zero symmetrical linear functional, then phi is a positive if it's M bar evaluated. Of course, the definition of the positivity by the following identity. That phi of F1 Fk is greater than or equal 0 for every for all that element Fs is greater than or equal 0. That preserve the compositive. Next, or in turn, we show one of the properties of that related with the evaluation characterization of symmetrical linear functional phi under the condition that A here is assumed to be uniformly complete unital closed F algebra of Rx. And phi is with the condition that phi be a no-zero orthosymmetrical linear functional. Let firstly we recall here what does it mean by subalgebra A of Rx is said to be inverse closed, respectively bounded inversion closed, if whenever F in A and Fx difference to 0, respectively modulus of Fx greater than or equals 1 for every X in X, then the inverse of F belongs to A. Also, let's we call that a multilinear mapping defined on M-fold Cartesian product of Archimedean real space A to an Archimedean real space F, or here not necessarily F be just be a vector space, not necessarily a real space. phi is said to be orthosymmetric if phi of the catables element of the n-fold Cartesian product A is equal to 0 whenever this catables contains a disjoint element. So let's return the proposition. If we take, as we say, we take AB uniformly complete unity closed F algebra of Rx, and the bound inversion and phi be non-zero symmetric linear function on the c-fold Cartesian product A, with K is again greater, not a number greater than or equals to. If phi is a multiplicative, then it is 1 bar evaluated. In turn, we show another feature of the evaluating characterization under the condition that phi is also non-zero symmetric linear functional. And here A is assumed to be uniformly complete unital inverse closed F algebra of Rx. So we have that if phi is multiplicative, then it is 1 evaluated. Let's we give that the attention about the last two proposition. The converse of the last two proposition is not correct, because there is a contradictory example. It's similar to the example that will be illustrated in next result. Now let we show in the following theorem one of the first properties. We show in the following theorem that the studies in the last two proposition can be improved to grade that a fact or with impact fact. It seems like an extension for the aforementioned result of Garrido and Gomez to extend that for the multilinear case here. So if we take X be a non-empty set and A be uniformly complete F algebra of Rx with unit 1, it's the same mean that we say that F algebra with unit or that unital F algebra. So let phi is not orthosymmetric linear function with K is again greater than or equals to. If phi is a multiplicative on A, then phi is m bar evaluating under that the additional condition m here is greater than or equals to. Next, we show the converse of the latter result. We separate this result from the last one to show that we can do more, and we get that wide impact result. So if take X also be a non-empty set and A be uniformly complete F algebra of Rx with unit 1, phi is non-zero symmetric linear functional with K is again greater than or equals to. If phi is m bar evaluating for that additional condition m is greater than or equals to, then phi is a multiplicative on A. More than that, it's a lattice morphism. Now I'm going to apply the previous results to the polynomial case. And before that, we need to some prerequisites. Let me mention that which we call representation theorem for the orthogonally additive and homogeneous polynomial. So there is many research about this representation through Sanderson and other authors. Let we mention one of that nicely theorem due to Koshraeva, which I think she is here with us. She proved that every order bounded orthogonally additive and homogeneous polynomial that acting between an Archimedes spaces into convex Born-logical spaces, it can be represented by that the composite of an order bounded linear operator and a special homogeneous polynomial that plays the role of the power law function that absent in the vector lattice. And very recently, we give here one of the Knightley theorem due to Miluchin and Doray Abdurraouf, which they prove that if P or extend that the last result for continuous orthogonally additive and homogeneous polynomial with phi be its unique continuous associated symmetric Miltonian mapping of B by the fact that if E be a real spaces and real space and F be a Hausdorff topological vector space, then P can be represented by the composite of the continuous linear operator T and that the nth power function F. Hence, B is induced by its associated symmetric Miltonian mapping phi by the same but representation by the composite that of the continuous linear operator T and the product of F1, Fn, which also is orthosymmetric, such that here T defined on the n-fold product of that relatively uniformly complete real spaces E into Hausdorff topological vector space F. Here, that the multiplication of the product here is not the Cartesian product. Be careful, we take that. The multiplication under consideration is the F algebra multiplication of the universal completion of E.
Okay, I beg your pardon, but unfortunately, I need to ask you to conclude.
I'm sorry. What?
I need to ask you to come to an end.
Let me load my sound. Wait. Yes, welcome.
I just need to ask you to come to an end soon, please.
Wait.
Your time is almost up.
Okay. But just we are in the final of the presentation. In the following lemma, we give so quickly we give that the two results. In the following lemma, we give that the relation. It's one of our basic results, which we give that the relation between the homogeneous polynomials P and its associated orthosymmetric Miltonian mapping phi for the evaluation characterization and the multiplicativity characterization. By the following, that if A be uniform complete unitary F algebra of Rx and B is a continuous orthogonally additive homogeneous polynomial defined on A, we have the following assertion. P is a polymultiplicative on A if and only if it's a continuous associated orthosymmetric Miltonian mapping phi is multiplicative. And B is M evaluating, respectively M bar evaluating on A if and only if it's a continuous associated orthosymmetric Miltonian mapping phi is M evaluating, respectively M bar evaluating. As an application for the previous lemma, we have the following corollary that for the same assumption, we get that some properties for the polynomial for the polymultiplicative polynomials correlation with the previous result for the Miltonian case by the same result for AB eclipses F algebra of Rx under the boundary version. If B is a polymultiplicative, then it's one bar evaluating. And for A, B inverse eclipses F algebra of Rx. If B is a polymultiplicative, then it is one evaluating. And these implications are not irreversible. So that if we consider that A contains the constant functions in the space of continuous real functions on the interval 0,1, and BB continuous orthogonally additive homogeneous polynomial defined on A by the integral of the K power F power K in X, then it's clear that P is one evaluating that by the using of the classical intermediate theorem value, but it isn't multiplicative. Finally, we are concerned to give the polynomial version of the aforementioned result of Hodgman and Vector. In particular, we give that the polymorphisms which under condition are polymultiplicative. So if we take AB uniform complete F algebra with unit element 1 and P is a continuous orthogonally additive common genus polynomial P defined on A, whose a continuous associated orthosymmetric Euclidean mapping phi, then polymorphism P is a polymultiplicative if and only if P is M bar evaluating for that the conditional here on M is greater than or equals to. And our talk is based on the following monographs. So thank you.
Okay.
I'm sorry
thank
because
you.
I'm take
No,
more time.
Thank you for your. Thank you. Does anyone? Well, let's thank the speaker. And does anybody have any questions?
So I have one remark that in the first slide, when he's giving the historical background, the professor who wrote the article of with Boulabiar is not Tommy, but it's Toumi, which is a Tunisian professor and not an English one.
Okay, I'm sorry. Yes, I know it's Ali Toumi.
Yes, and not Tommy.
Okay, I know him. Yeah.
Can I ask a question?
Okay, welcome.
Hello, everybody. Thank you for your interesting talk. I just want to ask you about when you were presenting the representation result, in what sense do you mean the multiplication? I mean the power.
The power is the product algebra. It's not it's the normal product, which we know the product operation. We mean that F power n, that means F times F for n times.
Okay, in Hausdorff topological vector space, yes?
Yeah.
Okay, thank you.
Okay, thank you.
No, but how can you make a product on topological vector space?
This is what I was asking. I mean,
yes.
The first
but
definition
I think that
is
the product
is
in the Ries algebra, I think. Yeah?
I know. I mean, the definition for the first one is given for the general case, given on subalgebra of Rx here, and the result after that we take it for the F algebra. Here we provide that the F algebra product. Of course, because we have that the domain is F algebra. Here we have that the product is F algebra product. Yeah.
And the range is also an F algebra?
The range, no. Here the range we take that the real file over the real file.
The real line?
Real. It's with the real value.
Okay.
Okay.
Okay, are there any more questions?
Yes, I have a question.
Okay.
If I understand well, the M evaluating map and one evaluating map are defined for subalgebra of Rx.
Yeah.
But in the last result, your last result.
Last result, yes.
You take the general F algebra, I think. So, yes.
You talk about this theorem, yeah.
Yeah. What does mean M evaluating here? Because it's not a subalgebra of Rx.
As we know that Hodgman and the Vector, they provide that every relatively uniformly complete and closed Archimedean F algebra is a subalgebra. By their results, because here That's the reason of we use the uniformly complete F algebra, the uniformly complete, and the F algebra here.
But Yusuf, I think that the F algebra are not subalgebra of R of X.
It's not
The definition of what is his name? Anon. This is the first definition.
The first definition is general case. I said that general case, not.
We have Busquets with us. He can answer us.
And here, there is many reasons here to use the uniform complete and that F algebra here under the condition F algebra, because as we know that the functional calculus it's also works on the uniformly completeness, and that F algebra with unit here to get that some property of the semi-prime F algebra. But be able to get our result.
Okay. So, is everybody happy with everything now? We should move on to our next speaker. So can we end this?
Thank you, Jonathan.
Thank you, Fateh, for your talk.
Thank you.
It was very nice. Thank you.